Hi, Ryan, and very nice of you to come on here and talk about fire.
Thank you so much for having me. I'm so excited to do this.
So I want to talk to you about two things because, you know, I try to keep up with the research and so on, and I see topics and basic two things that got my interest. You wrote a paper together with a friend or colleague, or maybe just you, but at least, but you were part of it at least. About two things that interested me. Both it was backdraft and it was small scale modeling. Yep. And I do in teaching, I love small scales of lots of things. I want to talk to you about that. And I want to talk to you about specifically backdraft. So, I'll jump straight into it. Like what, when I say backdraft, what do you think? You know, what's the first thing that comes to mind for you as, you know?
Well, when a lot of people hear backdraft, first thing that typically comes to mind is the movie from the 90s.
Yes, the research movie from the 90s.
Yes.
Yes.
Yeah. But I mean, the one thing I do love about that movie is it does bring to light something that people are just not aware of just, you know, when people think of a fire, they might think of like an open flame, like a campfire, but it's so much more complicated than that.
Yeah.
And the rapid dynamics of how things can change at the drop of a hat is just, it's wild. And one of the great things I get to do here at NIST is I get to kind of explore those wild phenomenons like backdraft. So when I think about backdraft itself, what I'm mostly thinking about is I think about an isolated room, or I think about an isolated enclosure.
Yeah.
Imagine, if you will, there's a room that there was a fire in, and the fire has kind of gone out because there's not enough oxygen in the room to sustain it. However, within that room, it's still hot. There's a lot of unburned fuel. There's unburned ash. There's smoke. And a lot of times, from my understanding, when there's a fire rescue team arrives on the scene and they suspect a backdraft happening, they're looking at the shine on the windows a little bit. The other thing that they start looking at is these isolated enclosures is the breathing of the room. And what I mean by that is you might see creases of the door where you see smoke kind of puffing out and then kind of air coming in. And when a backdraft actually occurs, what happens is that hot, fuel-rich room, you have some opening that opens all of a sudden and air rushes in and it mixes with that fuel. And if there is something that could ignite that mixture such that it's a flammable mixture, it can result in a spark. It can a kernel of a flame that then propagates through the entire enclosure and then rapidly exits that opening from which the air came. And if somebody's standing right in front of it, it can result in a fatality, a huge safety risk, or property loss, because these deflagrations happen rapidly. And, you know, over the past several years at NIST, I've had the pleasure of exploring backdraft and conditions conducive to backdraft, and we can talk about all the variabilities of that. And, you know, how can we potentially identify tools that provide more information other than intuition? So backing up a little bit, one of the things that I'm part of at NIST, I'm the project lead on our Smart Firefighting for Tactical Decisions project. Now, what is smart firefighting? I get that question all the time. And smart firefighting breaks down into cyber physical systems that provide information to some user or to some system that improves situational awareness and safety to an occupant or somebody involved in a fire scenario. And it breaks down into gathering data, processing data, and then delivering data effectively. And we've had technology for decades that can provide so much information and gather data, sensors, detectors. And the interesting thing is now, with so many different ways that we can process this data and how fast we can process it, it can start making, it can start processing that information so that you deliver it to an incident commander, a firefighter, for a wearable device. And that's pretty powerful, so that they can make more effective decisions that reduce the workload, that is safer, that is more informed, that might help search and rescue. And that's pretty powerful stuff. And we started thinking about, as opposed to like a smoke detector or other sensors that are out there, let's chase after something that, from a research standpoint, hasn't really been fully fleshed out. And that's where backdraft really comes in. And the goal in 2020 was, can we develop a sensing tool that samples or provides all these different measurements when combined together can provide some predictability of, hey, if you open that door, if there's an opening, backdraft's going to occur, or here's the likelihood of backdraft occurring. So, getting into what measurements are important, I talk about this isolated room, right?
Yeah.
And heat, how hot is something? How fuel rich is something, meaning it's oxygen depleted. There's only carbon dioxide, maybe carbon monoxide, methane, a lot of unburned pyrolysates if you're burning solid materials. And, you have this starved component, and what that creates is a different density within the room. So we think about density. I don't know how technical you want me to get.
Yeah, you go as deep as you want to go.
Perfect. Oh, I love it. I love it. But when we talk about density and we think of like oil and vinegar and there's separation there, imagine you have this separation of those components and you have density, discrepancies from on one side of the door, which might just be cooled air, and the other side of the door, which is this hot, rich, fuel-rich environment. And when you open that, air's rushing in. And what's driving the rush in of air is a gravity current, a discrepancy in density that's forcing air to come in. And then you create these eddies of mixture. And that mixture can be flammable, especially when it's presented to something that has high energy or amount of heat. And that can combust if it's flammable enough. And that combustion can then expand and then go out from where the air came. And some things that we've looked at is, how fast air moves in. And we're going to talk about scaling a little bit, I know. Yeah. And how fast air moves in, how it mixes, plays a critical role in getting an idea of if something is the likelihood of something actually combusting and then resulting in a backdraft is going to occur. Yeah. So, when we did these experiments, we've done already over 500 different experiments. We actually did develop the tool that can provide some prediction of the likelihood of backdraft occurring. But the data that we use to do it is only with a reduced scale enclosure. So what I mean by a reduced scale enclosure is imagine a meter by a meter by a meter and a half box. And you have
Americans go like,
yeah. So if you're stateside, 3 feet by 5 feet approximately.
Yeah.
And the idea more or less is we have this door that you can control pneumatically to open up and close, so no one's near anything. But what we did is we're burning gas fuels, solid fuels inside this enclosure to create that high temperature, fuel-rich environment and create that density difference. And, you open the door up and air rushes in. You're making measurements of temperature. You're making measurements of fuel to air ratio, oxygen concentration, carbon dioxide concentration, all these things that characterize the fuel scenario, not the scenario, but the enclosure conditions really, really well and accurately at different heights. And that provides an idea of the generalized conditions inside the enclosure such that it creates a bigger density difference for air to move in. Now, let's say, for example, I'm talking about the velocity of the gravity current. In the cases that we ran, we were running a spark igniter in the back because we wanted backdraft to occur. And the solid fuels, we would just have hot embers. If they didn't cool enough, they would act as ignition sources. But imagine, if you will, the length of it, which was approximately a meter, we doubled it or we tripled it. So why should that matter? Well, the gravity current as it moves in is being driven by the density difference. If you change the distance, how much air comes in and rushes in, there's a total mass of air that's moving in. It could push out a lot more fuel, meaning that by the time it gets to the back, there might not be enough fuel for a backdraft to occur.
Yeah.
All of it might have rushed out to the point where there's a minimal amount that there is just some small flame that doesn't propagate, causing a deflagration. And we haven't done those experiments, but you could do that through a model. And we've started to look at, you have these internal conditions of temperature, fuel composition, size-wise, and how that actually affects the mixture resulting in a deflagration. Not to say that, if you made it longer, it's always gonna never happen. That's not necessarily the case. You could have it be such a big density discrepancy that it's faster for the air to move in, meaning it's more likely to get to the back before enough fuel escapes. Does that make sense? Have I lost you yet? Are you bored?
No. I'm just, you're ranting here, and I love it. So I'm making mental notes, so going back to certain topics.
Yeah, sorry. I love talking about this.
No, it's super fun because I since I play with small models when I do training and so on, and I have basically not an ISO size of the scale, but it's about 70 centimeters, about 60. So it's a little bit smaller. Yep. With that, I have several compartments that I put in sequence and so on and do training and so on. So a lot of it relates back to my experience doing backdrafts and explosions and so on in those models. So it's great. No, because we can take this opportunity to go back, because you said you're starting to do backdrafts, looking at what are the conditions basically, and trying to find which are the critical parameters of getting that backdraft to happen or not. Is it the fuel ratio? Is it the temperature? Is it what is the right mixture to get into that range? And of course having that ignition point. When you go back to the sort of the initial starting point of where you wanted to, sort of the assumptions you had going into this, what were sort of your initial thoughts on, I think these will be the key factors that's going to sort of be highlighted in when we're looking at sort of the data and sort of the research and books and everything. This is going to be the key things that is going to dictate if we're going to get a backdraft or not.
Yeah, that's a great question. So, I mean, I keep circling back to this thought about a fuel-rich and hot temperature environment that's oxygen depleted. So what I mean by that is that the composition, if you break it down to all the molecules that are in there, there's not a lot of oxygen in there, but there's still a lot of nitrogen, water vapor, carbon dioxide, but there's a lot of fuel. And the reason why that's critical is
fuel, just to clarify, when you say fuel, what do you mean then? Do you mean the furniture on the ground? Do you mean actual vapor?
Yeah. So from an experimental standpoint, obviously, you doing experiments, and probably the demonstration when you do it, it's natural gas, right? No,
both. It could be propane if I'm feeling wild, but mostly it's vaporized wood. It's pyrolyzed wood.
Right. So let's go back to how fuel is generated, right? So, we have typically in our experiments a gas burner, but in certain cases we actually did wood cribs, not a baby's crib. I got to make that distinction sometimes, but stacks of sticks in an organized fashion.
Yeah.
And I think some people, when I talk about this stuff, and the definition of fuel is kind of interesting there, because when you burn these things, it could burn directly from the fuel source itself. But if you look at it on a very, 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 very small scale, what's happening is you're getting pyrolysis happening. And pyrolysis essentially is breaking down those cellulosic components towards flammable, volatile species or pyrolysates that can be combusted. And when we're generating these things, that's actually some of the other work that I'm doing now with wildland fires. We can talk about that too if you're interested. But
wildland, not interested at all. Rope rescue, not interested. It's just structural firefighting. That's the only thing that matters.
Well, the interesting thing though is that when people think about that kind of stuff though, and they think about even just wood or cellulosic material burning, it's like, oh, the fire's out. But the interesting thing is, it's a smoldering fire, but you're generating still other species that is not just carbon dioxide. And a lot of cases, if it's an underventilated fire, and this is another key word, is ventilation, underventilated, it can suffocate the flame, but it's still going to generate a very, very large amount of fuel because it just doesn't have enough oxygen, but it's still breaking down those components to generate pyrrolysate and combusted fuel from a solid fuel.
Yeah.
And, backdraft, the conditions that lead up to this phenomenon happening is you will have, let's say in a house, you'll have maybe a furniture burn or you'll have something happen. But if it's isolated, it's basically going to take, the flame's going to take all that air in the room and burn it up. But it's still going to be hot from the radiative feedback. It might be hot from just not being cooled down. to the point where it's still generating this volatile combustible gases off of the solid fuel. And all those things build up in the room, like carbon monoxide can be generated into a room structure and can be combusted, right? So if, all these other components like methane, and it breaks down to very simple molecules inside an enclosure that are combustible. And that's what creates that fuel-rich environment, even if you're burning something as, a wooden crib. And, one of the things that we did when we did these experiments with the wood cribs is we used something called a gas chromatography system to measure, to basically detect and measure the components of the volatile combustible species inside that enclosure. Yeah. And you're finding hydrogen, you'll find methane, you'll find acetylene, you'll find these things that are being generated because they're not complete combustion processes. They're not enough oxygen to actually combust them. So they just stay there and float in there in the environment. They might get vented out, but if there's not oxygen, they're just going to sit there. And that's what creates that fuel-rich environment.
So when I read studies, there's like when backdrafts and some backdraft studies, there's a lot of talk also about what is a dominant fuel to sort of create a backdraft. And some say, oh, it's the level of CO, it's the level of methane, it's the amount of soot particles, and when you looked at, because you chose to, for instance, use propane and was it more methane gas, and you also do solids. You chose those gases to sort of as a fuel source. That's not what it ends up in the air. It's just the fuel source. Right. But what was the intent of creating in the air to sort of get the fuel state that's in the air, the ready to burn state? What was the goal of creating there?
So it's interesting because a lot of people, I'm going to give you a very complex answer. I'm sorry.
Sure.
Yeah, but a lot of people in backdraft world try and use these signatures of CO or carbon dioxide or like methane as a gas that's indicative of that's the answer right there. Yeah. But one of the keywords that I mentioned is about ventilation. And a way to characterize ventilation is something through the equivalence ratio. Or do you know the equivalence ratio?
Yeah, so but explain it.
Yeah. For those of you who don't know at home, the equivalence ratio more or less is this idea of a fuel to air mixture normalized by a stoichiometric coefficient. So in other words, if I have an equivalence ratio of 1, that means there's a perfect ideal balance of fuel and oxygen such that when it combusts and breaks down, it's just going to generate CO2 and water vapor. If I have an equivalence ratio less than 1, it's going to generate more oxygen in the final product because there's more oxygen than there is fuel. If it's greater than 1, it's the other hand. It's going to generate more fuel than it is oxygen. And in the 90s, NIST developed a device called a phi meter. And for our friends across the pond, phi meter. So there's always a debate of whether it's phi or phi. And, as an American, I'd say phi.
Phi.
There you go. Bum. But the idea more or less with this device is that you could extract from in an enclosure, even if it's isolated or an open environment, and it could provide you a reading of the equivalence ratio. Yeah. Meaning it could provide a ratio of fuel to oxygen such that you get an idea of, if a combustion is going to happen, is there more fuel than oxygen? Is it generating more? And we didn't necessarily
regardless of the fuel mixture you have.
So that's a very, very good question. There was a first generation phi meter that measured something called the global equivalence ratio. And I'm getting really nerdy now.
Yeah, great. Just don't dive into
it. There's a paper I wrote, and there was no co-authors on that paper, it's just me, about different definitions of the equivalence ratio and how they're used in fire science. So when we talk about the global equivalence ratio, and I think in the paper I refer to as the compartment equivalence ratio, the idea is that let's say I take an extraction, I have a sample of gas in my enclosure. The global equivalence ratio is going to be all fuel components combusted and non-combusted, meaning like it could be, if I'm burning methane, it could be methane. but it could also be carbon dioxide was converted from methane. It could be carbon monoxide converted from methane. And then that ratio compared to all oxygen components combusted and uncombusted. So it is a global value that really takes into account the trace of gases that are just still fuel, but also converted from the fuel.
Yeah.
A local fuel equivalence ratio, which is more traditionally aligned with the combustion community, is just if I take that gas mixture from the enclosure, I'm just looking at the fuel components and the oxidizers. I'm just looking at the oxygen. And that is the local fuel equivalence ratio that aligns with a traditional equivalence ratio. So going back to my story, NIST designed this device called a 5-meter feed meter in the 90s that basically measured the global equivalence ratio. And what they were trying to do at the time was they were trying to get a sense of how much ventilation was going into the compartment, air through the door, fuel introduced from a gas burner, and they were trying to correlate that global equivalence ratio to CO generation. Yeah. Because in my opinion, one of the holy grails of fire science is trying to develop a robust fuel-independent correlation of predicting CO for computational models and just get a very nice curve of this how much you're going to get. Yeah. And
because you will generate CO if you start having lack of oxygen. It's a correlation towards how much oxygen, how much flow you're getting into the door, and so on.
Exactly. Yeah, but also, carbon monoxide can also be generated also if there's some oxygen available too. Yeah. It's not a perfect reaction. No. A lot of cases we hope, but nothing's perfect in this world. What are you going to do?
So you have lots of fuel here, and little oxygen, but over here you have oxygen. It's just chaotic mixtures inside. Yep. We're working with averages here, and
right.
Local differences mess up the system.
Yeah, but what happened was when we started talking about Backdraft, the global equivalence ratio was like, hey, this might be a great way to characterize ventilation and look at these components. But it goes back to your original question about, okay, you have one type of fuel. How does that play into a fuel mixture, especially when you have solid fuels and all the thing? Well, the benefit of the design that we have is it's agnostic to the fuel mixture. So we essentially have a technique that you sample gas, it combusts inside a reactor. We know how much oxygen was introduced into that reactor. We have excess oxygen to combust the rest of it, and we're making another oxygen measurement downstream. Because you're able to make that difference in oxygen measurement, it doesn't matter if you have a fuel mixture. It doesn't matter the composition. It's independent. Yeah. And if anybody wants to check my math, there's a paper I can send out that basically breaks down that, the composition of that fuel package doesn't matter, meaning that you can measure simultaneously the global equivalence ratio and the local fuel equivalence ratio simultaneously and in real time. Yeah. So I can get an idea of how much fuel is still residing relative and how much fuel has been combusted and uncombusted relative to how much oxygen's left combusted and uncombusted. But with a new design that I designed in 2021, I can also get this local fuel equivalence ratio in real time where I can get a perfect equivalence ratio of fuel to oxygen, uncombusted, without actually knowing the fuel composition at all. And in fire, that's so powerful because especially if you have solid fuels that you're combusting, fuel mixtures are a wide range of components. And boiling that down to a single value that is agnostic, that doesn't have to know the value of the composition is amazing. And what we were finding is with this new design that I designed in 2021, we could start mapping out the actual fuel component relative to oxygen in that mixture. Yeah. And from there, we can introduce that as a parameter that's critical, as opposed to looking at a signature component of like methane or carbon monoxide or carbon dioxide. Now we have a research tool that basically provides you an idea of the exact nature of a fuel to air mixture that is in an enclosure that could be combustible. Yeah. So you can almost track flammability. You can track how much fuel is in there. You could make a certain assumption. So that second generation feed meter, I skipped ahead a little bit, but that second generation feed meter that we developed in 2021 has been an amazing, powerful research tool that really has been but a big significant parameter in when we're talking about predicting backdraft, because I can characterize how rich the fuel is. I can characterize how depleted of oxygen it is. The other cool thing is with this design, I can make an assumption about the inert gases in there. And if you think about, the flammability diagram, there's a tertiary triangle, right?
Absolutely.
You know what I'm talking about?
Yep.
I can map out within that triangle where we are in a flammable mixture, just looking at the local fuel equivalence ratio and the nitrogen measurement, because I'm making kind of a indirect nitrogen measurement downstream, such that I have all those three components to get an idea of, hey, it's flammable in there. And that plays into explosion. There's a lot of different other applications that we haven't explored, but with Backdraft, it was very successful.
But just you say you measure nitrogen. Do you also measure water vapor and the moisture content in some way, or is because huge variability?
Yep. So the interesting thing is that think about mass conservation, right? So you have a sample gas coming in. You know how much mass flow that you have coming in. And because of that, it all combusts, all the fuel combusts. Water vapor also might come in if you're sampling from a hot environment and it's condensed out. Now, with the second generation design, past the reactor, there's a flow check, which is high temperature. So it's checking the flow rate at a higher temperature, which means it's including water vapor. We then condense the water vapor out, and then we measure the flow again. So did I lose you yet?
No. Then you can get it out.
Exactly. So you have a difference in flow. If you know water is scrubbed out here, that's the difference in water. And then you make another measurement of oxygen, carbon dioxide, and nitrogen past that second check flow. And that, not nitrogen, excuse me, just oxygen and oxygen and CO2. And that provides you basically all the information that you need, because with that second flow check, you know how much mass of oxygen there is, how much mass of CO2 there is. And by default, nitrogen, because there's nothing left. Or when I say nitrogen, I really mean inert gases like argon and nitrogen. But so therefore, if you've backtracked, then you have water, you have carbon dioxide, you have oxygen, you have nitrogen. So you know all the components that are being generated from that reactor.
The biggest components.
And because of that, that basically gives you all the pieces to the puzzle to get an idea of the components, once they're combusted, that are in there of that extracted sample gas. So that's how you're indirectly measuring nitrogen, and you can also back out water levels. And one of the cool things that we saw,
and that means you can also measure. Let's say you're burning wood, you can also measure. Of course, you can measure the wood when it's burning, see how and check moisture content before you burn it. But in that case, you can also look at. You can also take away the water coming from the wood when you do the sampling.
So we it depends on the moisture content of the fuel, I think, because we haven't run that, but theoretically, if there isn't a lot and you're not sampling, because you're just pulling it from one point. If you don't sample in the right place, you might have a limitation there. But one thing that we did see is there's a conference paper I wrote a couple of years ago about can we actually how does suppression affect backdraft? And from our measurement technique, all we're doing is in that enclosure, we're running these experiments, but we're shoving a ton of water in there, and that cools it down. And also, you're throwing off that density measurement. But the cool thing is, we're actually able to measure the water content, that difference in flow measurement. You could see that there's a bigger difference as you introduce more water into the environment. It's just there are detection limits for a device, and one thing that we're iterating now is we're trying to make it so we can ingrain this device inside an enclosure as opposed to having an extractive measurement from that enclosure. So we're trying to make it smaller and more portable. Imagine like somebody's basically carrying like a bread box, and they're sampling from there, and it's just kind of all in one inclusive that's just providing that information. And then you're introducing water, and you can kind of see the effectiveness of how you're introducing that suppression. But moisture content, unless it's very soggy fuel and even that's going to take a while to ignite, right? It might be hard to kind of get that idea. But there's other ways to measure water too, like with humidity probes and things like that can be incorporated in there.
I just know from experience and reading stuff that, of course, moisture content, both just as it is and what's created by the fire is it's a big component on how things burn. So I have so in one of the training facilities I have, we dry the pallets before because so it's because when you throw it in basically it's a pyrolysis generator that pumps fuel into the training facility, and it makes just a huge difference in terms of flammability on the smoke and so on, and the quality of the smoke for training when you do this, because you're losing 10, 20, 30% of water just contained in the pallets.
Right. Yeah. It's, I mean, when you look at that, when you go back to that flammability diagram that I was talking about, the way that some people interpret it on a very basic level is like there's just nitrogen and argon in your gas phase, but you're really CO2 and water vapor are accounted for there. Right. When you talk about those inerts, those are accounted for in those inerts components. The thing is that, in certain cases, I think for like a large event, the dynamics of throwing that off, there has to be a lot of water content coming from it. And there can be. But I mean, sometimes I think about water levels coming off of like trees or untreated wood. Someone on a ppm level. But I mean, right? If it's evaporating off, it's not necessarily like on the scale of like percentage wise, is it?
In the smoke, I don't know. I mean, I don't know exactly how fast you can vaporize it in proportion to all the pyrolysis gases. I just know. I mean, I know it makes a huge difference in terms of how hard it is to light the pallets and how the quality of the flammability of the smoke afterwards. But I don't know how. If you do a moisture content, let's take a wet pallet or a dry pallet, and you try to vaporize them, and you look at how big of a percentage difference in terms to how much moisture content is it in that smoke. I don't know. I've never seen a measurement on it either. To be fair. Yeah.
When we burn some of the stuff for like tree burns that we do for our wildland urban interface group, moisture content of the tree itself is always considered for. And these are massive, firs. I like to look at things from my perspective on the gas phase of it and kind of extracting from there. But pyrolysis of those components would definitely play a role into kind of combustion, especially like at a heated surface level. It's just the measurements that I make aren't as refined to that scale. No.
I think it's just moisture is just because when Sweden started dealing with like high pressure water systems and how they suppress fire using basically vaporization to gas and gas acting as an inert gas when it's superheated above 100 degrees. We know for a fact that works great to suppress fires. But then you're of course introducing large quantities of water in comparison to how fast you're vaporizing it in the pallet. So I just don't know, again, the ratio of if you take a wet pallet and you just, put it down to a lot of radiant heat and measure basically what's the proportion of water compared to that. I definitely, it will be a difference. And I mean, I always am fascinated about how insane the output of energy you can get from fire, but still it's such a fine, delicate heat balance of staying alive. Like you have this massive fire and it just drops below a certain temperature of the flame, and heat release rate goes to it goes very high, but boom, goes to zero. It's you're just reaching that thermal threshold of the flame, and just boom, it's just that's chemical. It's such a balance.
It's really that's really interesting because I mean, when we ran these backdraft experiments. And we're doing these isolated enclosure stuff, right? We have a camera on the inside that's viewing some of these flames. And what happens is, because you're choking it, essentially like you're depleting it of oxygen, and these combustion products are also just kind of making a really inert environment. The flame self-extinguishes. And if you have a gas burner, I mean, it's just pumping more fuel in. For a solid fuel, we see a rapid drop in that happen as soon as, because it's consuming, the heat release rate is so big. and the space is so small, it consumes all the oxygen almost instantaneously.
Yeah.
So like that equivalence ratio measurement that I was talking about,
Yeah.
you know, you shut that door, it shoots up.
Yeah.
And then it just stays there because it's like there's no oxygen to keep moving and keep combusting. So all this fuel is just saying, I'm just hanging around.
Yeah.
But the wild thing is, like, when we talk about enclosures, and I just wrote a conference paper about this, about ghosting flames. You know anything about ghosting flames?
Yeah, it's separated from the I think I know the concept, but yeah, go ahead, explain it.
It's when you get to this, you talk about a balance. When you get to like very underventilated components, meaning that the more fuel is being pumped in than there is oxygen, you know, the flame is going to self-extinguish, but there is a transition in certain cases where you see the flame trying to keep itself alive by falling off of a burner or off of things, and it's traveling locally within the region of its enclosure, trying to find oxygen. And we
without
found
anthropomorphizing. It's not trying to find something, it's just reacting, right?
Yeah, it's not cognizant. You're right. Yeah, I like to interpret it as that. I mean, but it is the point where it's where the oxygen pockets are available, and it's just kind of maintaining that reaction. Yeah, there's no fire spirit or anything like that.
It wants to, as to say in the Backdraft, the fire moves because it wants to.
Yeah, exactly. Yeah.
Nobody, we call it dancing. I mean, fire instructors, we call it just, fire angels, dancing angels. When you have that, loose pocket of ghosting flames, when you get those, and it's beautiful. If you create a smoke layer in a fire behavior prop and you ignite it somewhere else, you don't ignite it at the initial fire, somewhere else, and you get that perfect mixture where it's not really flammable. It's not super lean, not too rich. It's just in the balance, so it's really slow and it creeps around. And it's this sheet, and it just kind of, and it's. I mean, to be honest with you, I think it's a thing of beauty. Oh, like, for seriously,
sure. I love staring at it, and just hovers there.
Fire porn, that we call it.
Yeah, and in some cases, like you can see. I mean, some cases you can see it just burning blue. Yeah. Meaning like it's not generating any soot. It's just this kind of pure flame.
Especially if you do it in a gas, like if you do it like in a propane layer, like no smoke. Yeah.
But we started finding these really interesting cases where, okay, we're seeing ghosting flames, and this wasn't completely an isolated compartment. We started playing around with the vent. There's a lot of people who have done that in the past. Of either looking at like a vertical vent or a horizontal vent and kind of playing around with the ventilation factor to a flame structure and looking at the fire dynamics there. And with this equivalence ratio measurement, we were actually kind of able to correlate when these ghosting flames occur and the equivalence ratio. So like you can get an idea of this instability, this intense point where this balance starts getting out of whack. To the point where the combustion breaks down and it transitions to a ghosting flame that is, just moving through the compartment. The other cool thing that I've started working on that extends beyond the backdraft work, but it's still pivotal to it, is extinction. So, we talk about extinction in terms of when the flame goes out, self-extinction of you're stuffing it out, you're stuffing the fire out, not necessarily instigating suppression. But can we track, based on the ventilation parameter or the equivalence ratio parameter of like how that fuel air ratio is changing, or the fast rate of which it's changing, is that indicative to the flame going out or the flame diminishing? So like if one thinks about a well ventilated environment, you're burning something in there, the flame structure is being maintained. You can use correlations to actually look at the flame height. You can get an idea of its heat release rate. It's consistent because there's enough oxygen. But as you transition to a realm or a region where, you're starting to suffocate it a little bit more with less oxygen, and it transitions to a smaller flame with less heat release rate, the smoke layer starts to descend down from this compartment, and there's less oxygen moving in, you can start actually mapping out, based on what we're finding with the equivalence ratio, the extinction times of when the flame goes out or when it starts diminishing and breaking away from its typical structure. Which is pretty interesting, because if you think about sensors and you think about technology that could be implemented, and you could start mapping that from these correlations, that provides insight into fire dynamics of a room without any visual observation.
Yeah.
And that to me is pretty powerful. I mean, you could see, a handheld device, and this circles back to smart firefighting. I just like to push my own product. But this idea more or less of you're providing information from these correlations, it's processing that data. And from all these measurements, you're getting an idea of, okay, the flame structure is diminishing here. There's less oxygen here. This is presenting actually a bigger hazard because there's more fuel here. This is getting into the realm of backdraft because it's fuel rich and there's no flame at all.
Yeah.
Or, it's signaled. I mean, the ghosting flame is a very interesting scientific phenomenon, but I think from a firefighter standpoint, it's rare.
Oh yeah,
right?
Operationally,
it doesn't necessarily happen.
No. Well, to be fair, it probably happens a lot more than we see, because probably so you don't see anything. Right.
So but the information of. Sorry.
No, but it is, like you said, it's probably rare. I mean, again, it's that balance you have to find. You're probably at the range where the fire is either basically suffocated, or it's burning well. Right. It's very rare to come at this this exact time where it's just struggling, in that. So it's like a probability perspective. It's really hard, so I guess that's one of the reasons I think it's very rare that you see it.
Yeah, but imagine all of a sudden where if you have sensing technology that is using some of this mathematics, and then all of a sudden it's telling a story of the fire scenario when no one's observing it. Yeah, and it gives you this idea of, hey, kind of what happened, because when we look at, one of the other projects I work at, I'm getting a little bit away from enclosure. So if wrangle me back,
I will drag you back in a minute.
But imagine, we look at forensics, we look at analysts past a fire scene. So the fire's out. We're doing deconstruction. We're breaking things apart, and you're looking at soot patterns on walls. Yeah. Right. I mean, a lot of arson investigators and forensics analysts and investigators have looked at these things to kind of reconstruct a fire scene of it started here, moved here, the V shape pointing towards, and a lot of people look at that. But imagine all of a sudden you might have more sensing technology that provides insight into kind of maybe what happened without anybody kind of observing it. To me, that's pretty powerful stuff, because it tells a story of maybe the fire location. Maybe it tells an idea of how the flames spread and what kind of dynamics were going on. It's pretty interesting. And I've worked on some soot deposition stuff that tells the more interesting story, but we're not here to talk about that. So
no, but it is interesting. Of course, I think that, I know for a fact that there's been a lot of misconceptions in that, in terms of not understanding flow paths and so on, and see where misleading signs where soot is burned off, because it's not where the fire started, it's because where the air came in, and not understanding those kind of that. But no, we're not going to go into that. I want to backtrack again, because we talked a lot about, and I want to get to scale modeling also, and more about backdraft. But we talked a lot about fuel and oxygen, and of course ratio, and nitrogen, inert gases. But I want, we haven't talked as much about heat, so I want to backtrack again. So that component, when you started going back, you talked about, assumption is hot environment, and that being one of the triggers. Now, so talk about heat and the importance of, or lack of importance of heat, for that matter.
So we'll circle back to your original question. Yeah. When we look at parameters, ventilation, equivalence ratio, you can dive into that, but heat is obviously the other component here. We're heating up this temperature. So you're calculating density. Density, obviously, temperature plays a critical role in density and driving that force a little bit different. So, heat and those components. I think we could
just dive into that, because generally I think there's a normal misconception that that the fire compartment, you talk about gravity current, it's normal misconception it's driven by pressure differences, which is also true, but it's a gravity current about light air being and cold air coming in.
Yeah, but so pressure, there's a normalized density difference if you look at like a Froude number, which is driven by buoyancy essentially. And really density can be calculated from PV equals nRT, right? If the ratio relative to a mass over the volume, and then you have P over RT, and those correspondence of pressure and temperature play a role into density. Yeah. So when we talk
but pressure is pretty much sort of a non-existent in terms of that, in terms of structure fires.
Yeah, exactly. So what's driving this flow? What's driving this difference, right? Is it this pressure difference that's driving the velocity? This gravity current can be measured that way. But in this case, temperature plays a critical role into that density measurement, that density discrepancy across the open door. So, what we started playing around with when we started doing these experiments was dumping in water. And I kind of already talked about this a little bit, but cooling off a lot of that environment to see we have the same, we'll talk about time in a little bit, but we're modifying that density component a little bit, and how is that playing with the gravity current as it comes in? Yeah. So with these experiments, you're creating that fuel-rich environment. It's a lot of fuel in there. You dump a lot of water in there. There's inerts, but also it's cooling off the temperature. Yeah. And what happens is that's slowing down the gravity current because the density difference is shrinking. Yeah. So therefore, it's slowly moving in, giving more fuel time to escape. So then when it finally gets to the ignition source, when it ignites, nothing necessarily happens.
Yeah, and the way that we were able to leaned out.
Yes, and the way that we're able to track that is through the heat release rate or the energy projected from the combustion when it does happen. And we found that as we're introducing more fuel into the component, water vapor into the atmosphere and into that enclosure, it's slowing down the gravity current, the combustion's less, then the heat release rate is less, right? And essentially it's just because less things are burning, it's not as much of a fire that's happening. It's a smaller fire size. Heat release rate corresponds to fire size.
But now we talk about cooling just the gases and everything, not the fire itself.
So there's a second component to this, because when we talk about introducing water, you're also changing the components of the composition. The other component that you can do to lower the temperature is wait. Yeah. Is you just wait. The temperature kind of just, if you wait long enough, it's going to basically fall to a low temperature where the composition is different, but that it's still low enough that temperature is not contributing as much to the density difference, such that the gravity current slows down.
And now we're talking about a closed door.
A closed door. So imagine in our environment, if in suppression world, you could just have a spray nozzle or you could have a sprinkler system that just shoving in there. But imagine you have a closed door, you don't have that opportunity. Yeah. If you wait, you let things cool down, you're going to get to a lower temperature, which is going to affect the gravity current as it moves into the compartment, and it might slow it down. So when we talk about the solid fuel experiments that we did, we played around with how long to wait for temperature to cool. Yeah. And, we're finding, and there's a little bit of caveat here, which I will explain, that if you wait long enough with that temperature, that it slows down the gravity current, nothing comes in. With the solid fuels, there's another component to all this, is the ignition source. Yeah. So we ran experiments where with a solid fuel, you're letting things cool down, but no ignition was happening because the embers that were generated from that environment were cool enough that even if there was a rich fuel mixture, a flammable mixture, nothing was happening. Yeah. So we modified those experiments a little bit to have a spark igniter, so you're energizing that. Yeah. But you do see a difference of, as things are cooling, the gravity current slowing down, it is affecting that, similar to like the composition, and less as air moves in, there's more fuel coming out, such that there can be an event where you have combustion, but it won't result in a deflagration, meaning it won't result in a backdraft. Yeah. So, providing these exercises of, I'm going to wait because, temperature is very, very hot. The density difference is going to be great, causing gravity current to move in very quickly, or, suppressing it or venting it in a very small fashion such that you're depleting some of that fuel and you're not necessarily doing that. I don't think the ventilation is action taken where backdraft happens, right? If someone suspects a backdraft, typically what happens is it's wait. What is the official action?
You're opening up a can of worms here. It depends on who you ask and what's the. I mean, typically a lot of America has been, vent for life, vent for fire. Right. So it's been ventilation to prevent backdrafts, which I think that most of America is starting to like. If you think it's a backdraft scenario, massively venting is probably not a good thing. You get a backdraft or just a massive fire, maybe if it just resumes combustion. But so waiting has never been the solution for any fire department in the world, because every fire department is kind of in a time, at least a perceived time hurry. But I think the biggest difference is over the world, and Sweden, in the 90s starting to play around was, exterior cooling with piercing nozzles and so on. Right. Cool it down and create thermal ballast in there with steam, and then vent it out, because then you take away the hazard. Now that still is because, for other reasons than fires, what happens if there's a victim in there? What happens to the environment? There's other questions, but simply from a fire behavior perspective, that of course would be the most obvious.
That would be the simplest thing.
Yeah.
Right. But that's the cool thing about the technology that we're talking about, that we worked on, right? Yeah. The goal of developing a tool to predict the likelihood. Yeah. So, we identified these things of heat, equivalence ratio, and all these other components. And the idea more or less was, if you had a sensing technology that either would, as you said, a puncture that you could sample from and extract a little bit in the overfire region, or just in the enclosure itself, you have those things, and it's providing you real-time feedback of, the likelihood of backdraft is this, because this is all the conditions that we're kind of measuring from that component. Yeah. And think about the actions that we're talking about. We're talking about ventilation. We're talking about suppression in certain regards. Yeah. If there's an occupant in the room that's very fuel rich, that's very hot, that might be another talk for discussion about the livelihood of that room. But in certain cases, you could instigate some tactical decision. You could instigate some way to say, I'm going to cool this, I'm going to vent it. And if you have that tool still, you could see the effectiveness of that tool, because it's providing you feedback such that I'm measuring all these conditions of inert gases and temperature and the fuel-air ratio. And I can see that's rapidly changing, meaning that my model essentially is now saying that the likelihood is shrinking, meaning that my tactics are being more effective. So, providing more information about that is useful. It's very, very useful for how we do tactical decisions when we're dealing with these hazardous events.
Yeah, we'll look at, if the objective is to find those benchmarks to at least anticipate the likelihood of a backdraft happening. I see, would it be if you have if the sensor technology is so cheap that it sort of can be incorporated at least to start off in, high valuable industries and hospitals and so on, where you could go and you come as a fire department, you arrive and you see this is the smoke detector that's deployed, and I can see of course how likely is it to backdraft. If I can see oxygen concentration is 20%, temperatures rising, but I can just, because of course, when the knowledge of backdraft, sort of the problems with underventilated fires, started becoming a reality, and firefighters started to understand it, it became sort of a defensive thing to not ventilate at all. So, the standard approach, I teach that as, if you don't know if it's flammable or not, it's just a lot of smoke. So you as quickly as possible get to the fire and suppress it before you can ventilate. But if we knew that we could ventilate, which I think that's the most important answer. If we can get a data that says this environment is not flammable, if we could have that, you could start vent straight away. That would be such a big benefit if we could do that.
Yeah, and I guess the question that, as a scientist, and you're probably already recognizing this, I get lost in the weeds pretty easily about a lot of different stuff. And I think the one thing that good scientists need to do is they need to sometimes take a breath and ask themselves, what is the question that we're trying to answer? Yeah. And especially when we're talking about products, it's, how much information is needed for me to get an answer about something? Yeah. And sometimes for something like we're talking about with a backdraft forecasting device, that's a very expensive answer. That might be very expensive in terms of time or cost or all this stuff. But yeah, the one thing that we're starting to work on now is tailoring a little bit more of this device towards looking at flammable mixtures and just getting a general approximation, because that might not give you all the information that you need to say definitively, like this is going to happen, but it provides more information to make better decisions of this is a flammable mixture. This is a flammable component. There's a lot of flammability. If I'm sampling all these other areas, you know, as opposed to looking at, you know, like a FID, a flame ionization detector, actually measure the concentration. I'm going to use this as an approximation to get an idea of the fuel-air mixture, quick and dirty. And that's what we're trying to simplify now with that smaller devices. You know, something deployable that's providing information more or less. That's not an expensive answer. You know, does somebody want a $5 answer or $1 million answer? I think something robust. You want something small. But provide that information.
Yeah. But I think that both, in terms of that, you know, do I think it's valuable for firefighters to have portable devices, for instance, to measure, like, you know, you can see where you're at, and you'll get a flashing light that says, "Hey, you're in a flammable mixture." Would that be awesome? Absolutely. You know, 2 thumbs up. You know, I need to start working my stream and so on. But also, of course, the high dollar version where we have all the buildings, active systems being controlled by the actual. You know, this is the time to vent, and you go like, no, the fire is growing faster than the vent can handle. Now it's time to close the vent and start introducing nitrogen, for instance. Like you could build stupid systems like that, but you can also build them from actual data saying that, hey, you know, we're using the measurement tack that makes the most sense. You know, like because you don't want to vent a fire that's underventilated, and you don't want to close a fire that's oxygen controlled down, because you're bottling up smoke and creating smoke hazards. So you want to know both of them. And as a firefighter, I think that for me, I think that the opposite would be most valuable, saying that this environment is not flammable, because then we could be more aggressive with ventilation, which is the tool we have for saving property and people. I say that, but it's the fear of, I don't want to start breaking windows here because it might be flammable. Yes, it might be bad, and that might be a bad outcome. So definitely that. But you know, I see that, you know, as a researcher, I would go for both of them. How can I make it cheap to become portable? And of course, in every smoke detector, you know, like and you connect it to a central intelligence. We're getting AI, and everything's going to be connected in 10 years. So the sensors will have somewhere to send the data, which is, you know, like everything will be connected and so on. So that will be much easier. You will have AI interpreting all that data too. So just getting the sensors and everything would be one important piece of it. But I know you have limited on time. So I think it's interesting to look at those sensors, and going back to before we get into scale models, going back to your assumptions, because we talked about the fuel. You know, of course, we need a lot of fuel to make it happen. We need temperature. Because of temperature driving the gravity current, but also, of course, the higher temperature you have, the more flammable it is, the more energy you have.
Sort of. Yeah, I mean.
Well, why you say sort of? I would say, if you have the same mixture of the inerts and fuel and oxygen, if you make it hotter, just a mixture, it would be more flammable. It would be easier to ignite.
Yes. Yeah. It's a combination of everything, not necessarily just solely temperature. No. That's just one component. If given everything the same, a hotter environment will be easier to ignite. It will be. Yeah. There's more energy dumped in there, making it easiar to flame. Yeah. 100%. I'm with you. Yeah. It's not just like, yeah.
No, hot air doesn't burn. Well, technically it could. So some molecules could probably burn in hot air.
Yeah.
You can have oxidation. But anyway, so you have those components, and just based on my experience from playing, those ratios, again, one is not enough. You have to have some. You have to have some oxygen. You have to have some heat. You have to have some fuel, and you play with those ratios. And depending what fuel it is, you can have, for instance, demonstrations I do. When you have wood smoke, you need a very high temperature to really be able to get wood to burn. The wood smoke from burning, it's very hard. As soon as you mix in synthetics and get a bit of plastics, you can have combustion in the smoke much easier down to lower temperatures in the smoke and so on. So of course the fuel type and how much soot and carbon monoxide you form from it makes a huge difference. Was there any assumptions when you went in about sort of why backdrafts occur that you sort of tweaked during those 500 tests? Why do we get backdrafts, or when do we get backdrafts?
Yeah, I think one of the things I will say, and from a scientific standpoint, is that a lot of the conditions that we identified. So, for instance, like we varied how much fuel you pump into that compartment.
Yeah.
And all that. One thing I think, to keep in mind is people try and look for a critical single term value. So a lot of times when you look at backdraft components, a critical temperature, a critical CO to carbon dioxide ratio, a critical, in certain cases, equivalence ratio.
Yeah.
But the things that I think we need to keep in mind are, it's not, I don't think personally it boils down to just one value of something, because the problem is you're oversimplifying it and you're overgeneralizing it. And, we're talking about heat. We're talking about not a lot of oxygen. We're talking about a very fuel-rich environment. I think a combination of those things is critical for conditions that are conducive to backdraft to occur.
Yeah.
And also at ignition source that, when presented with a flammable mixture, will ignite such that a critical mass inside an enclosure is going to deflagrate and then result in a fireball going out that enclosure. If, even looking at cases where you have propane versus methane and the distribution of that fuel inside that enclosure, that can also play somewhat of a variable to whether or not backdraft is going to occur. The location of the igniter might also play a critical role. The gravity current as it comes in is coming into the base floor. And if I have no ignition source, but if you move it further up, you might see a small delay in when ignition occurs, because those eddies are forming as they come in, they're mixing in, and then it's circling up. So and you can see this in some of the computational models that we've done. It's pushing out that fuel kind of back and then all the way out, so it's making the C. So, the presence and the location of the ignition source is also kind of a critical component to all this thing. Yeah. It's a very complex phenomenon, because you have buoyancy-driven flow, you have critical fuel mixtures, you have the spot location of ignition where there has to be a flammable mixture for that to occur. But those combined together really do tell a story of this is what it takes for backdraft to occur. In our experiments, we modified the fuel component, the fuel distribution, we modified the density, we modified the spark location, we modified even the time of ignition. So we had a spark igniter for about 500, we've done 600, 500 of these experiments. Yeah. We had a spark igniter all the way in the back, but we delayed when that was turned on. And in a lot of the cases that we were running, you have air moving in, it's mixing with the fuel that's residing in that component. If you delay when that spark igniter goes off, that's going to offset backdraft occurring. In some cases, it's not going to occur. Yeah. And you start seeing discrepancies of these variables that do play in a role. It doesn't mean there's a critical threshold. It doesn't mean like, if I always have this spark igniter here, it's going to happen. What it tells you is that is a component to backdraft occurring. Yeah. That is a condition that needs to be considered when backdraft occurs. Now, from a firefighter's perspective, no one has control over where the igniter is, right?
No, so, we don't know, and we can't control it.
Right, and then also, there are cases about ventilation. There are cases about how the size of the vent We also modified our door to we reduced it by 20% opening area, and you kind of see there's a little bit of discrepancy of the backdraft and the energy when the deflagration occurs, because it basically changes the flow of air coming in and fuel coming out, and that also kind of plays a role in a difference. So you look at these two groups and you're looking at backdraft occurred here, backdraft didn't occur here. Yeah. Why is there a significant difference here? Well, that means that there are components to consider, but the big ones for what we're trying to measure, and I think from a practical standpoint, are heat that's measured through temperature, fuel component or fuel to air ratio, and characterizing that very well. I think the inerts in the environment, also kind of looking at nitrogen, which plays a little bit of a smaller effect. And those I think are the major ones that we saw and identified. And also getting an idea of the CO2 measurement. That's where global equivalence ratio comes in, and that kind of plays into inerts, because that's also like the history of, there's not a lot of oxygen here, but a lot of the components in here are inerts, are combustion products that have already been combusted. It's not necessarily fuel. But combining all those together really tells the story of, this is a vitiated environment that could combust, that has a big flammable mixture in it that could result in a backdraft. But there's other critical components that from a scientific perspective of the location of the igniter, the size of the opening, the density that you have in there that's not necessarily the fuel component. Those are also considered. So if you're asking what is the one thing you need to know for backdraft, there's not just one thing. It's extremely complex phenomenon that's happened, that you're really seeing, the flow field, the combustion, the deflagration on the outside that has all of these different components. But the three ones I would say are heat, the fuel air ratio are a big thing, and the inert gases, and kind of get an idea of that.
That makes sense. I gave up some years ago of trying to anticipate bad fire events and just simply try to prevent them. It is because to me heat became the number one factor, because it makes flammability easier. It makes it faster. It's everything. So heat makes it worse, but it's not an indicator of flammability. But it is an indicator that we have the ability to cool, so we should cool.
Yes.
It's just so that is this is sort of trigger for we need to cool. The one that scares me more, if it's really hot, I know that I can cool it, and if I have something hot that's burning, and I cool it down, it's the likelihood of if it's burning again is extremely small, because we have taken away a lot of the energy and we have mixed it with steam and water everywhere. It's very unlikely. The scenario that scares me is cold smoke, because we don't have the ability to add more thermal ballast with steam, because we can't vaporize water. We can't cool it down because it's already cool. So the only option we have, whether or not it's flammable, is to vent it. Which is, and then you just hope it doesn't explode. So cold smoke has become, and particularly because of the increased use of like EPS styrofoam type insulation, you get smoldering fires in the walls. You get this white wispy smoke, cold smoke of just pure unburnt.
Can I ask you a quick question?
Yeah, sure.
Are you seeing a lot of cold smoke in electrification systems?
In what? Cold smoke in
energy storage systems.
Yeah, of course, and super highly flammable, and it's ridiculous. And if we get into battery fires, that's a whole new area. But yeah, but yes, and I've done a fair bit of that too. But yeah, we're not going to dive on that bullet. But it is a huge problem, of course. If you're going into a structure and it might be light wispy smoke, and it might come from batteries. Now it could be explosive. So light wispy smoke, regardless of that factor, but that just made it worse, is more of the things that make me nervous, because we have too few control measures to implement as firefighters. But again, if you get to raging fire, I just know that if I can suppress it with a hose line, I'm pretty much good.
Right. And it's not like you have a big nitrogen tank sitting on the engine.
No.
That you could just, I'm going to dilute it with just, an inert gas, because that might be the other solution, right?
Yeah, that is the actual typical solution for silo fires.
Right, exactly.
Because you could, I mean, you don't have nitro at hand, but you can order a nitro truck or something and fill it up. Yes. But to not run out of time, I want to talk about scale fires. So
that's fine. Sorry.
You have 15 minutes. So you did these experiments in an ISO small box. I love small boxes for training. Talk about the limitations and the advantages of using small scales, in this case, for you to do research. Why did you do just burning a big house, and how can you get away with burning tall doll houses?
Yeah, I mean, large scale experiments. And when I talk about large scale experiments, I'm talking about that are realistic to reality. That like, I'm burning a house, I'm burning a 2-story structure. I'm trying to get an idea, because I mean, Dan Goddick, if that name sounds familiar, he's a fire protection engineer, brilliant man. And he did some work in the 90s with Backdraft, I think for the Navy or maybe somebody else. But he was doing heptane burns in a sea container. And, he talked about looking at critical mass of fuel. And he looked at, again, the flammability diagram. And he's like, if you're looking at critical mass and it passes this flammability region, well, obviously, that's going to be an event where, ignition can occur, resulting in a backdraft. And it's hard from an experimental standpoint, especially with fire. It's to do what we did 600 of these experiments. That would not be possible if we were doing sea containers. I'm telling you now, we built something robust, and the compartment that we're talking about has withstood those 600 experiments. It is still standing and has done very, very well. And it provides a lot of additions. But from an experimental standpoint, large scale experiments require a tremendous amount of resources. It's not everything that's on hand. It requires a lot of attention. There's also a higher risk associated with it because it's larger, so there's a lot more things that need to be controlled when they're presented. And one thing that I've been getting in the back of my mind is a lot of stuff that we've looked at, and like the models and the mathematics that we developed around, forecasting backdraft or looking at flammability, does it translate to scale? And, it'd be nice to kind of not necessarily do 600 experiments, but it'd be nice to kind of look at a sea container and start looking at these things and applying the same measurement techniques to say, hey, we're still, and I'm not, we're not changing the ball game here. We're still looking at flammability. We're still looking at, the inert gases. We're still looking at the temperature on the inside. We can vary, but the challenge becomes a little bit of trying to scale that up. I talk about the equivalence ratio and how the phi meter came about. They were looking at the equivalence ratio, global equivalence ratio relative to CO generation. And, you look at something like a Purser furnace. I know you've had David Purser on the show before and getting an idea. He's a fantastic guy.
Oh God, I love David. And, but you look at these things. The Purser furnace is a nice ISO that you could basically try and get an idea of the yields of CO and other components by modifying the equivalence ratio inside a furnace and a reactor. But the challenge becomes scaling it up and trying to compare, the yields relative to the equivalence ratio. And it doesn't always scale because the fire phenomenon and the physics surrounding it aren't always captured and they're not always scaled correctly, such that, radiative feedback to the fuel surface and the generation of that. So when we talk about scaling of these things, it doesn't translate perfectly. No, you have one part of the material is like unaffected, and one part of material is almost gone, and one part is there's a massive differences in how.
And I don't want to say, a lot of stuff that David's done has been fantastic. And it's not saying that there aren't correlations and approximations that can't be made. I mean,
no, but that's for all the different materials you put in the oven. You see what happens if I do it here in small scale. But then you combine them or scale them. That's a whole new problem.
I think, if you look at one of the papers I wrote about the equivalence ratio, I take, just in the context of carbon monoxide, relative to the equivalence ratio, a lot of research has been done. And I take these plots, they're extremely messy plots, but I plot them all and they're like, okay, it's a fair approximation of getting carbon monoxide yields of relative to the global equivalence ratio. Where it starts getting more challenging is in underventilated scenarios, where you start getting to these drastic cases where combustion's choked, fuel is choked, and it starts having this wonky stuff. We talk about ghosting flames, and
you get secondary reactions, and
it changes the game of how those things are balanced. And that's the interesting thing about Backdraft. Identifying these components of fuel mixture relative to air and temperature. I think those are independent of scale a little bit, but the dynamics of the gravity current coming in, the presence of that ignition source, how things mix accordingly, because you're at a little bit of a larger scale, it does mean that you're widening the world of what you're trying to figure out. And simplistic values that you're getting from that, I think, get a little bit more challenged because of that. And you could simplify a model like CFAS that NIST has developed is 2-zone model, so you could really make these approximations. FDS, the fire dynamic simulator, is challenged a little bit more. We're trying to see, like, hey, if we extend this out, how does it mix accordingly? Where is the best place to sample to kind of make these assumptions from? But larger scale invites larger variability, and it's possible that sometimes it won't be as translatable because you're not accounting for that. And the best thing that you could do is try and make an assumption of what are the parameters. And I think that's why you're shooting at these questions at me. Yeah. What parameters are kind of key to translating scale? And I still think it's flammability of the mixture, looking at the temperature, looking at the inert gases in that component. And if you look at that, I think that still translates scale. It's just, are you still accurately representing the scenario such that you're going to be more firm about what's going to happen? Yeah. Small scale, it's easy. Meat scale, it's a little more challenging, but it's doable. Large scale, there's a lot more things to kind of consider. So those are things I think we need to consider if we're doing larger things, and start to make approximations. But it's hard. It's hard.
Yeah, and I think that's important. I think when I saw so small scales have been used in fire training for a long time. I don't know, 30 years maybe in various cases, and you build models that does something in specific. You build a model, for instance, to do backdrafts, and it's a small house, for instance, and you do a model that shows flow paths, or you build a model just where it's very easy, especially when I use some of the larger models. It's very easy to make the model do something that doesn't really correlate to reality. You can build a model to show something that isn't really likely to gonna happen. Oh, look at this! This is what happens because of just physics. Some physics scale down, but some don't. Like this, like distances, like how fast the air moves, or distance to the radiative heat source. Like that doesn't scale. Like if you have the fire 2 decimeters away, even if it's small, that's not the same as having a fire 4 meters away and so on. So some things doesn't really happen the way you do. And I see one issue with, I see models being used and people sort of doing research on models, see what happens if we do this, and then take away key things that happen. Like, oh, let's do this in the future when we have a house fire. Well, like, no, that's jumpy. I get nervous about that.
But I still think, though, that models are such a valuable tool because they
don't get me wrong. Yeah, absolutely.
Yeah. I think they provide a lot of information. The way for the backdraft stuff, at least, is I can't control my compartment conditions perfectly. No. Right? I can't kind of make a uniform temperature. I can't distribute the fuel differently. But in a model, I can. Yeah. And that can tell me a little bit more information that, like, trying to understand the fundamentals of this that are informative to the technology that we might develop from that, such that, hey, maybe when we're running these experiments, or maybe if we're going and deploying this stuff out in the field, here's the better way that we can make more conclusive statements. Yeah. And here's kind of the explanation, excuse me, about of why these things are happening. So there's a little bit more control there. But the tool of it, and I mean, FDS has been a fantastic tool for fire protection engineers, especially when it comes to performance-based design and all these other components, is, you get an idea of you get an idea of flame spread, but it's not always true to nature, right? There's still a lot of things that are kind of
it's from what I've seen, it's as soon as the fire grows beyond the point sort of origin, when it spreads out into the room, especially when it goes to another room, like we're talking 2 compartments, or at the point when the fire starts to become ventilation controlled, I think the model starts to become increasingly unreliable from what I see in at FDS. You have to make so many assumptions.
Yes.
You have so many assumptions. So basically you have to sort of know what's going to happen, and you can simulate that. But if you don't know what's going to happen, I think the odds of you finding out what's happening in reality, it's unlikely.
I think, well, I mean, in NIST, we love
if we're not talking about simple things like how, if I have a fire, what's the heat transfer through this steel beam? Like,
right.
If we're talking, what's going to happen if I light a corner here in a sofa? What happens if I light that on fire? What happens in the next room?
But I will say though, from an experimental standpoint, just to justify my job, it's more or less, we talk about NIST, we talk about measurements. There's a lot of uncertainty associated with that, and you're right. If we start going out the realm of what we know, the uncertainty is going to widen, right? And really, that's where stuff that I do comes into play. Like all the stuff that we've talked about, of transition to ghosting flames and extinction, that is informative to the existing models, and basically can help identify, hey, the extinction model that you have that's just based on the oxygen and temperature measurement, maybe we need to expand upon that a little bit more and refine that a little bit more. And, other measurements that we make, like if we talk about PAHs and the generation of those, maybe those fast kinetics aren't really necessary for certain things that we're trying to do. Maybe we're trying to generalize something to get an idea of flame spread. And that sometimes also plays into some larger scale fire models. But from I think, some of my postdoc work that I did here at NIST was informative to like gas species prediction of pool fires. And we were doing similar to things of gas extraction measurements and analysis using gas chromatography to actually inform FDS. And actually at IFSS, the International Association of Fire Safety Science, they use that data set as a benchmark that fire foam and all of these other models that were developed across the world at Ghent and Maryland that were saying, okay, here's a very refined experimental data set. How do our models compare to this? And having that conversation about what are we missing? What are we improving upon? It's always rapidly developing, but that's why it's critical for both parties to talk to each other and provide this information, so that we can improve it and get better about it so that we're a little bit more real to life.
Well, and it's going to be way easier when AI starts to be implemented more to take this enormous amount of data and have AI basically make sense of it. Import this data and make a better calculation and anticipation.
Well, I think we talk about the NIST. The one thing I always struggle with when I'm writing a paper is like comparing other experiments, especially when you're talking about Backdraft, because it's like, well, they did it a little bit differently and they did it a little bit differently. And like, there's discrepancies in what we're finding because it's different sizes and different stuff like that. And I think reporting measurements, very, very well and trying to really capture that and marking the bounds of which they have been recorded and developed are critical, are very, very critical when we start talking about the development of these models, because mathematical models that are implemented in FDS, empirical models, we have to know the bounds of what they apply, how they apply accordingly. For fire protection engineers, like CO generation, Dan Goddick, I think he did work with Latimer in the 90s. They have a temperature-based CO production relative to an compartment, the equivalence ratio. But there are challenges associated with that because the data they developed the empirical model on was limited by what they tested, right? So
absolutely.
That's something to think about when we start talking about these kind of things,
No, I think that, and don't get me wrong, I think that, and again, the data because data is so hard to, as I'm so bullish on AI, the ability to make sense of large quantities of data, to do correlations and get something that's gonna. I think that's fascinating how that's going to be implemented, and I for sure think that.
I'm not the AI guy. I'm sorry. I don't know much about that.
Oh, damn you, Ryan. You're not as nerd as I thought you were. I ran your reports through AI before we sat down here to see what it's spat out. It's just fascinating. It's absolutely fascinating.
Yeah.
I sat yesterday and I had some questions about it because I'm building a training facility and I was going because I'm using. I have a smoke generator, and I'm gonna go like, how, give me some, and just off the cup ask questions for AI, see what it comes up with. So I was asking how to improve smoke production in the combustion chamber. How do I do this and this? And the results was just like, holy crap, it's getting good. And these are very specialized things. It's not like what's the how do I how do I build a Lego set? It's complicated. It's specialized things that aren't, and it gave me fantastic answers, even though it's not a specialized AI for that. It's just your general, like ChatGPT or Gemini. No, I think that's gonna be awesome. I want to so before you go, we get back to scale models, because there is I just want to. When I think about scale models for training, we talked about limitations and advantages. Of course, the same goes for training. Advantages of it being cheap, and you can replicate it, and you can do it all over. You can protect the structure and so on. So that's fantastic. Now we have opening size comparison to the room size. You have to make a huge difference, and you tend to, like your ISO model, you have the opening size is relatively to the room size is much bigger. I know there's research papers on that alone, and you just use a model that's been verified that works. So you have those, and then you have time, of course. Everything it's compressed in time compared to a big volume. So time is big one. Distance is a big one. The opening relationship to the volume is a big one. Is there anything else I'm missing there that I think is important? If the fire instructor uses models to teach things, what we give some tips and tricks and think about this to accurately portray fire behavior in scale models.
So we have the opening size relative to the compartment, the time component. Yeah. What was the third one again? I'm sorry.
Yeah, just distances, like how far things are apart. Which is natural, but
space. I mean, I would, when you're teaching these things, I mean, these components are critical. I would also say, I mean, think about additional vent components that are unaccounted for. I mean, you could have windows that are in the room and that provide additional. You could have, instead of just one single ventilation component, you could have two. Other suppression technology that's out there. I think the ignition source too, and the presence of ignition source is also valuable. So we talk about time. I mean, that plays into the temperature in the room going down, but also if you have hot embers or you have less sparks, I mean, that also kind of plays a role into the fuel package and the development of the fuel package. It's from a practical standpoint, those I think are very, very good components to consider. And I think it's also key to know how, we talk about these major conditions that are conducive to backdraft, but how those parameters that you're just mentioning about opening size and, time, how those really play a role in affecting those parameters, and understanding that I think is pretty critical, because then that's informative to directed action.
Yeah.
Right. That's going to kind of dictate, what's going to happen. I think teaching these kind of components, I sometimes, I mean, I curiosity. I mean, I think sometimes when you speak with people about the equivalence ratio, eyes glass over and goes there a little bit maybe. But I think, that fire triangle that we have of heat, oxygen, fuel, I think that's another key component to making it a little simplistic about you have this component of these components are critical when kind of capturing that fire scenario, that fire configuration, and getting an idea of what's going on there. And the positioning of everything and the actions that could potentially be taken to dump out those heat. Because I mean, I'm not a firefighter. I'm not a volunteer firefighter, but the timescales that I know of are you have to make these decisions, and to overcomplicate it with so much information that you're trying to keep track of, it can be very, very challenging, and in many cases distracting. Yeah. So making and simplifying these decisions, I think, is critical, so that if a scenario is suspected, especially a hazardous scenario is suspected, they know kind of these components to look for that I think are critical, that are important. And I mean, time is sometimes out of our hands. It's you have to make a decision. You don't have 20 minutes to wait. And that, you have to make a decisive decision that's going to, again, affect those conditions so that it's safer, right?
Absolutely. It's the best job in the world to be a firefighter, but it's also one of the more challenging ones because you do a lot of guesswork. We guesstimate a lot.
Yeah. And I mean, one of the things that I try and pride myself on is just, you and the rest of the fire service across the world, and I mean, in the United States, are our stakeholders. Yeah. And we're trying to, find different ways and different technologies and different information that we can engage that informs, so that the guesswork becomes a little more clear, that uncertainty gets a little more resolved.
Yeah, no, it's awesome. I think I love it, and I hope NIST continues to be a big proponent, a big producer of fire research data, even if it's some of it is very niched and only be read by nerds. But nerds aggregate it and produce it to something more meta, a meta, and hopefully introduce it into some kind of like education and so on.
It develops, yeah.
Yeah. No, I understand you need to go. So thank you for your time, Ryan. Keep it up with the research. I'm going to read it when you deploy new FIFO models also. Thank you. Have a good day.
Thank you so much.
Yeah.
Yeah, this is great. Thank you.